So when you get section 14.7, which is when you're finding whether a surface has a maximum or a minimum or a saddle point, we do this thing where we set the partial derivatives equal to 0, and we find all of our critical points that way. But there's a reason we're doing that. And the thing we're actually really doing is we're setting the gradient of the function equal to the 0 vector. And so to kind of provide context, let's talk about this one example and kind of see where that really comes from. So here's the function we were looking at last time. It's this little mountain thing that I like to draw. It's f of xy equal to 9 minus x squared minus y squared. And we're going to look at this level curve up here, where z is equal to 4. And I'm going to draw it down here in the xy plane. So here's my level curve. And, sorry, excuse me. I want to really kind of figure out at this point here. Well, so really the big picture is I want to know what the derivative is in this direction. So, sorry, the direction I haven't given you here. So, sorry, I'm a little not flummoxed, but sorry, I've got a lot of things going on right now. I'm just like, need to take a moment here. So this point's the point 1, 2, 4. So this point here on this circle, 1, 2. This is the circle x squared plus y squared equal to 5, because we've set z equal to 4 here. And so if we solve for x squared plus y squared, we get 5. And what we're going to ask here is, what is the derivative of the function f of xy in the direction of v equal to 2i plus 3j. So from this point here, which is over 1 and up 2, I want to know if I go in the direction that's 2 to the right and 3 up, so kind of this way. If I go that way, what's the slope of the line tangent to the surface in that specific direction? So I'm kind of saying, right, if here's my x, here's my y, and I'm kind of going 2 in the x and 3 in the y, I'm kind of going like that way there. And I'm asking, what's the slope of that tangent line in that direction? So here's what we're going to do. We're saying, okay, so at this point here, what is the slope of the tangent line there? Well, what we're going to do is we're going to parameterize this vector here. We're going to make it a line. So not just a vector here. Let's say, I've drawn this vector poorly. I'm sorry. That's terrible. So let's parameterize v. Parameterize v, which is not too hard to do. It's just going to be, well, I'm at the point 1, 2. Oh, actually, sorry, I've made it look like that should go through the origin when it really shouldn't. That's my brain is, sorry, my brain is not braining so well today. This picture was fine without that part there. Sorry. Okay, so we're going to parameterize this line that actually doesn't go through the origin like that. So, well, we've got a point, we've got a direction, not too terrible. Our line here is going to be the x coordinate plus, we're going 2 in the x direction, and our y coordinate 2 plus 3 in the y direction. So there's a parameterization of this line. And what we can do now is we can say, well, if I want to find the derivative of this function in that direction, I can use the chain rule. I can say, well, my function f depends on x and y, but then x and y both depend on t, because this is really what x is in terms of t. It's really what y is in terms of t. So then, if I'm going to find df dt, it's really going to be del f del x times dx dt, plus del f del y times dy dt, just like we were doing last time when we were doing the chain rule. Same sort of little path thing. And then if we look at this, well, check this out. This looks a lot like a dot product. It looks like it's the dot product of the partial derivatives vector times dx dt dy dt. But dx dt dy dt is just the vector v, right? Dx dt is 2. dy dt is 3. And that's exactly the direction that we're taking this derivative in. And del f del x del f del y, this is the thing that is called the gradient of f. So if you have a function of some number of variables, it could be x, y, z, it could be 4 variables, it could be any number of variables you want. The gradient of that function is just each partial derivative in the right order, meaning like the partial with respect to x, then the partial with respect to y, and the partial with respect to z. You could do different orders, but typically it's going to be the normal order where we're thinking x in the I direction, y in the j direction, z in the k direction. And that is the gradient of this function. So then this is, I'm sorry, come on, you can fit. The gradient of f dotted with v, which is the directional derivative of your function in the direction of v. Now I missed a small little thing here because I didn't do something here. What we typically also want to do is we want to normalize v, right? Here my vector v is not normalized. So what I really should have done is said my directional derivative in the direction of the unit vector u is going to be the gradient of f dotted with u, where u is just v divided by its own magnitude. Okay. So in this particular example that we were looking at, where we have the point x, y equal to 1, 2, and the vector v equal to the vector 2, 3, meaning u is going to equal 2 divided by the magnitude of v, 3 divided by the magnitude of v, which is just root 13. Our directional derivative at that point in that direction is going to be, well, my gradient is, I didn't actually find the gradient. I should write down what it is. The partial derivative with respect to x is going to be negative 2x. The partial with respect to y is going to be negative 2y. Evaluated at the point 1, 2, dotted with my unit vector, which is 2 over root 13, 3 over root 13. Then we get negative 2, negative 4, dotted with this. When we multiply that out, we get, let's see, negative 2 times 2 is negative 4 over root 13. Negative 4 times negative 3 is negative 12 over root 13. So we end up getting negative 16 over root 13. Sorry, it's kind of hard to see there. What does this mean? This is telling us that if you're on this surface and you are at that point and you're asked to move in that direction, the slope of the surface in that direction is negative 16 over root 13, which is approximately negative 4.4. Meaning if you move 1 unit forward in the direction of travel, you're going to go down 4.4 units in the z direction. And if you turned around and went the other way, the derivative would be the opposite sign. If I said, okay, real quickly, what's the directional derivative if u is the opposite direction? Well, then you're really just going to get the literal opposite value. Then that's going to be positive 16 over root 13, which is approximately positive 4.4, which makes total sense if you think about actually walking on a hill, right? If you're walking downward and you turn around, the steepness is going to be the exact opposite, just the positive value instead of the negative value, or vice versa. Okay. there's a lot to say about the gradient, but again, he's not going to ask you about it. I don't want to spend too much of your time on it. So here's what I want you to really know about the gradient, a couple things. So the gradient of your function f is denoted upside down triangle, delta, nabla, I think I think that's what that's called. I don't know. I just say gradient. Literally, like if someone writes this, you don't say nabla f, you say gradient of f, because that's what we're talking about. And it is a derivative, a vector, and it's equal to the partial derivative. So it's del f del x in the I direction, del f del y in the j direction. Or if your function is a function of x, y, and z, it's the gradient of f equal to del f del x, del f del y, del f del z. But it definitely is a vector. And importantly, it is always perpendicular to our level curve. Yeah, that's what I want to say. So what I want to point out about this example we just did is that the gradient here, which, sorry, did I lose that piece of paper? The gradient here, which was at this point was -2, -4. The gradient is a vector that is living parallel to the xy plane, right? It's not pointing up or pointing down. It is in the z equals 4 plane that's parallel to the xy plane. So if you go back to this here, right, the gradient is actually pointing, sorry, I've ruined this picture here. The gradient is actually pointing towards the center of that mountain. So you couldn't actually, if this was a real like physical object, you couldn't actually travel in the direction of the gradient. You tried to travel in the direction of the gradient, you would start going up the hill and you would be forced to kind of move upwards as you still move inwards. So the gradient isn't saying you're pointing up, it's in the direction of travel that if you went that way, you would be forced to go up as steeply as possible. So the gradient is always perpendicular to our level curves. And two more things, I think. Yeah, two more things. So the gradient, and I know I said this last time, but I want to say it again, always points in the direction of steepest increase. So if I asked for this example we were doing at the point 1, 2, what is the direction of maximal steepness well, it's going to be just what our gradient was, which was -2x, -2y, evaluated at the point you're at, which is going to be -2, -4. Now, how do we know this is actually true? Well, it's actually kind of slick. So what I'm really trying to say here is I want to make the directional derivative as big as possible, right? I want to know what direction I have the most slope. Well, here's my directional derivative. It's the dot product of the gradient of f and the unit vector u. Well, great. We know how to calculate a dot product using another formula. It's the magnitude of the gradient times the magnitude of the unit vector, which is 1, times cosine of the angle between them. And if I want this number to be as large as possible, what's the largest value cosine can ever have? Right, exactly. So if theta equals 0, not that it really matters, like, so if the angle between your unit vector and your gradient is 0, then you're going to get this being equal to just the magnitude of the gradient of f when theta equals 0. So we actually learned two things from this. Thing one, the direction of the gradient actually is the direction of maximal steepness. And thing two, the magnitude of the gradient is that maximal steepness. So the magnitude of the gradient is the maximal value of the directional derivative. I think the first part's more important, that the direction of maximal steepness is the direction of the gradient, but it's also interesting that the maximal steepness is the maximal value of the gradient, or is the value of the magnitude of the gradient. Okay, so all this to say that when you want to find where a function, a surface, has a relative extrema or a saddle point, we do this by setting the gradient equal to 0. Because you're essentially saying the gradient, which is the partial derivative with respect to x and the partial derivative with respect to y. Well, to have a point where you have a relative max or a relative min, you need both those partial derivatives to be 0, so that we have essentially a tangent plane that is horizontal. That's what I'm really thinking about, to be honest. Like if you want this to equal 0, 0, you're really saying on my surface here, I want that point have a tangent plane where both the derivative in the x direction and the derivative in the y direction are both horizontal tangent lines that have slope of 0. So that's kind of a very abbreviated version of why we are going to do what we're going to do in section 14.7. To find critical points by setting the gradient equal to 0. I imagine your professor probably, he might, I don't know actually how to say it. He might not have said it that way. But that's actually what we're doing. We're trying to find critical points. So let's look at some examples of that. I know there's so much more we could say about the gradient and directional derivatives, but time is fleeting. So let's look at some examples that are not quite so, that might feel a little more tangible. Let's find critical points of the following function of x and y. 3x cubed plus xy squared minus 9x squared minus y squared. Now, I like to think of this, and I think it's worth thinking of this as we're going to set the gradient of f, which is the partial with respect to x and the partial with respect to y, equal to the 0 vector. But in practice, what people just use is they just write partial with respect to x equal to whatever the partial is. It's going to be 9x squared plus y squared minus 18x. And we're going to set that equal to 0. And we're also going to set partial with respect to y, which is going to be 2xy minus 2y equal to 0. And what we're trying to do here is we're trying to find all possible solutions that simultaneously solve both of these equations equal to 0. And the usual kind of plan of attack is to look at the equation that seems simpler to deal with. And in my opinion, that certainly looks like the second equation. So if I look at that second equation, I'm going to say, well, I can factor out a 2y. If I do that, I get 2y times x minus 1 equal to 0. So my solutions to this equation are either y equal to 0 or x equal to 1. And I want to be extra super duper clear about this. This does not mean that 1, 0 is a critical point. In fact, it is not a critical point, because if you plug in 1 for x and 0 for y in the other equation, fx evaluated at 1, 0 is going to be 9 plus 0 minus 18, which is negative 9, which is not 0. So we need both equations to be equal to 0 at the same point we're plugging in for x and y. But I just want to point this because it's kind of a common mistake to maybe like, oh yeah, I got a y and an x, those should go together, but they don't necessarily. So then we're going to take each of these potential solutions and sub them into the other equation. So if I start with y equal to 0, well, then I'm going to have fx equal to 9x squared plus 0 minus 18x equal to 0. I factor out a 9x, I'm left with an x minus 2. And so here I get two potential solutions. I get x equal to 0 and x equal to 2. So from setting y equal to 0, I have two different critical points. I have the point 0, 0, and the point 2, 0. And we can definitely, I think, easily see that if we plug in 0 for x and 0 for y into either equation, you'll get an answer of 0. It's a little more work to see that if you plug in 2 for x and 0 for y, you will get both equations equal to 0 as well. All right, let's find the other critical points by setting x equal to 1. So if we set x equal to 1, then my fx is going to be 9 plus y squared minus 18 equal to 0. Solving that, I'm going to get y squared equal to positive 9. So y is going to equal plus or minus 3. So I get two more critical points here. 1 comma positive 3 and 1 comma negative 3. So those are all of our critical points for this particular function of two variables. The second part of this is classifying. So we're actually going to, so you might remember from 21A, it's been a while since 21A, but in 21A, you actually had two different ways of determining whether or not a critical point was a relative extrema. There was the first derivative test where you'd be like, oh, the function's increasing over here, decreasing over here, so it goes from increasing to decreasing, you have a maximum. But there's also something called the second derivative test for critical points, which is that you can say, well, if the second derivative is positive at a critical point, then the function is concave up, meaning we have a minimum. Similarly, if the second derivative is negative at the critical point, the function is concave down, you have a maximum. And we're going to use a test that's analogous to that for functions of two variables. So here's what we're going to do. We're going to calculate what most people usually refer to as capital D. It is literally the determinant, which is something we haven't learned. You don't typically learn a determinant until you get to 22A, but you might have seen it before though. Determinant of the Hessian matrix, which is just the matrix of second partial derivatives. So really care, that's what that matrix is. It's the matrix fxx, fxy, fyx, fyy. And so when we calculate this capital D, it's going to be fxx times fyy minus fxy squared. Technically, it's fxy times fyx, but in these functions, those two mixed partials are always going to be equal to each other. So we just say it's whichever one you like squared. Okay, so then I need to look back at my function to find my second partial. So looking back here, my fx was 9x squared plus y squared minus 18x. So fxx is going to be 18x minus 18. Fyy is going to be 2x minus 2. And fxy squared, fxy is going to be 2y squared. Fyx is 2y as well. And I would say most of the time, I don't think you usually want to simplify this. It is not worth the effort to multiply this out because we only ever care about evaluating this thing at specific points. So I want to figure out what's happening at each of my critical points. So I've got the critical point 0, 0, and 2, 0, and 1, 3, and 1, negative 3. And then we're going to plug into our capital D here, which I don't really need to write again. And we only care about the sign. I don't care about the value at all. So we're really just trying to figure out, is capital D positive or is capital D negative? So I plug in 0, 0, let's see what we get. So D of 0, 0 is going to be negative 18 minus 2 minus 0 squared, which is positive. I guess I could say it's 36. So if capital D is positive, here's what that means. Here's what I think about it. For capital D being positive, it's not always the case, but it's often the case that fxx and fy actually have the same sign. So here's what I'm thinking about when I think about this. I'm thinking, okay, well, my function at this point The second partial with respect to x is negative, meaning I'm concave down in the x direction. My second partial with respect to y is also negative, so I'm concave down in the y direction. So at 0, 0 here, we've got something that's looking like, well, I'm both concave down in the x direction and concave down in the y direction. Not that it's exactly like this is just kind of how I imagine it. So we have a relative maximum at this point. So here's the usual interpretation. If d is positive, then you have to look at the sign of one of your second partial derivatives. So if we look at the sign of either one, it is negative in this case. And when it's negative, that means you have a, sorry, I'm running out of room here, a max, a relative max. So if d is positive, then you check either one of the second partials. And whatever their sign is, then you're just saying, oh, second derivative test, if it's concave down, I have a max. If it's concave up, I have a min. Let's look at this other point here. If I plug in 2, 0, I'm going to get, let's see, 18 times 2 is 36. 36 minus 18 is positive 18. 4 minus 2 is positive 2. And still 0 over here minus 0 squared. This is also going to be positive. And when d is positive, we either have a max or a min, a relative max or a relative min. Here, since my second derivatives were both positive, that means we are concave up. So here we were negative, which was concave down. Here we're a positive second derivative, which is concave up, meaning we're going to have a relative minimum. And then for these last two, I think we end up getting negative d values. Let's check. So I plug in 1, 3, I get d equal to, d of 1, 3 equal to 18 times 1 minus 18 is 0. So that whole part's going to be 0. And then minus 2 times 3 squared, that's going to be negative. And when d is negative, that means we have a saddle. We don't even care about what's going on with the second derivative. We know that we have a saddle. The idea when you have a saddle, it's not 100% exactly this, but it's kind of like you're in one direction, it's concave up, and in another direction, it's concave down. It might not be actually the x and the y direction, but there's some direction at this point where one way it's going upwards, the other way it's going downwards, and so we have a saddle point. That's kind of the actual literal definition of the saddle. Concave up one way, concave down another way. And then same thing's going to happen for 1, -3. We plug in 1, -3, we're also going to get 0 minus 2 times -3 squared, which is also negative 36, which is negative. So that's the whole gist with this finding and classifying critical points of a function of two variables. Let me spell it out just so we can have it more formally written. So for a critical point of your function of x and y, if d is positive, we check concavity. And either if fxx/fyy is negative, meaning we are concave down, then we have a max. If fxx or fyy is positive, then we're concave up and we have a min. On the other hand, if d is negative, then we have a saddle. And finally, the saddest situation ever, if d is 0, the test is inconclusive. That doesn't mean we can't necessarily tell. It just means you have to use other means to figure it out. Here is a classic example of an inconclusive one. F of xy equal to x to the 4th plus y to the 4th. So if I do this same sort of process for this function of two variables, the critical value, well, let's do it. So my fx is 4x cubed. Set that equal to 0, I get x equal to 0. For fy, I get 4y cubed, set that equal to 0, I get y equal to 0. So my only critical point here is the critical point 0, 0. And if we find d, which is fxx fyy minus fxy squared, that's going to be 12x squared times 12y squared minus 0 squared. And then if we plug in our critical point, we're going to get 0 times 0 minus 0, which is 0. So the test is inconclusive. However, I bet we could make a pretty convincing argument that 0, 0 is a relative minimum of this function. Because we know that x to the fourth plus y to the fourth is always greater than or equal to 0. Because we have even powers here. So since x to the fourth plus y to the fourth is greater than or equal to 0 for all points, we can see that 0, 0 is a minimum. It's a relative and actually absolute minimum, but we really don't typically care about absolute minimum or maximum. So people, there are other, often like there will be questions like this where you're like, well, we can't use the test, but you can kind of make a compelling argument based on things always being positive or always being negative. That's the usual kind of thing that happens when someone gives you one that's inconclusive and they still expect you to say something about it. All right, let's look at a few more examples because sometimes these things can be a little funky. Sure, that example is fine. Let's actually grab these other examples over here. I hid from myself. Yeah, let's look at these examples. So let's say we have the following of xy equal to x squared plus 6xy plus 10y squared minus 4y plus 4. All right. So I know we've done it one time. The usual process. It's always the same steps though. Just like in 21A when we were finding critical points and classifying them, same deal here. Find critical points and then you're doing the same thing every time to classify them. So my fx is going to be 2x plus 6y. I'm going to set that equal to 0. And my fy is going to be, let's see, 6x plus 20y minus 4 equal to 0. Sometimes when you do this, you can just get nice values like in the first problem we did, where like we got y equal to 0 or x equal to 1, and then we plug this into the other equation. Here, that's not going to happen. We're going to get kind of equations relating x to y, and we're going to have to plug that equation into the other equation to get our values. So I would probably do this by saying, well, 2x equals negative 6y, x equals negative 3y. That seems like the easiest thing to do. I'm always trying to pick the easiest thing to do for these problems because they can get algebraically messy. And then we're going to take that and plug that in for x in our other equation. So then we're going to get negative 18y plus 20y minus 4 equal to 0. So I've got 2y minus 4 equal to 0. So I've got y equal to 2. And then I plug that value back into the other equation. I say, oh, well, if y is 2, then x is going to be negative 3 times 2, which is negative 6. So my only critical point here is negative 6, positive 2. That's it. It's the only one. All right, the usual thing. So sometimes the usual thing is kind of boring. What I mean by this is if I find fxx here, it's going to be 2. Fyy is going to be 20. And fxy is going to be 6. There's no calculating to do here. I just have to determine, is this thing positive or negative? And then if it's positive, is it concave up or concave down? Let's see, 2 times 20 is 40. 40 minus 36 is 4, which is definitely positive. And so it's positive. And then based on the signs of fxx and FYY, this thing is concave up because my second derivative is positive. So fxx is positive, meaning we are concave up. So we have a minimum. So -6,2 gives a minimum. Sometimes people like to find the third coordinate of this, like they like to say the point is -6, 2, whatever you get when you plug in -6 and 2. Usually not what people ask for, but I think there's some web work problems that do ask you to do that if you're in the solids class. So just be aware of that. I think he had addressed that in the announcement as well. One thing you might question or wonder about is why don't we have to check both fxx and fyy if we know this is positive? Well, if this is positive, if d equal to fxx times fyy minus fxy squared is positive, then these two things had to have been the same sign, right? If these were opposite signs, you have a negative number minus something that's for sure positive, which would make it even more negative. So there's no way that this can be positive and have fxx and fyy have opposite signs. So if this is positive, then you're guaranteed that fxx and fyy must have the same sign. That's why we only check one. Which is nice. Sure, I think we did that one. Let me double check here. No, we didn't quite do that. Sure. Let's look at, oh, I know where. We got lots of examples that I think are interesting here. Yeah, there we go. So let's look at that one. That's y equal to x cubed minus 3xy plus y squared. I will say a couple things. Most of these examples are usually just powers of x and y kind of smashed together. Like you don't usually really encounter many other functions when you're trying to find critical points here. Because if you start introducing things that are exponential or trigonometric, critical values get very ugly very fast. So this is probably most of what you'll encounter here. Occasionally, sometimes someone can throw in like an e to the something, or maybe a reciprocal, but not a lot. Yeah, we got time for both of these. So let's find our critical points. Let's find our gradient, right? I'm really, even though I'm not actually saying that, we're technically setting the gradient equal to 0. So 3x squared minus 3y equals 0. And then the derivative with respect to y is going to be negative 3x plus 2y equal to 0. Which way to go? It's not always an easy question to answer. If I look at this first equation here, I can think of this as being 3x squared equal to 3y, or just y equal to x squared. And that kind of feels like it might be easier to plug into the other equation, which might be slightly counterintuitive, because if I looked at both these and said which one is the quote unquote easier equation, you might think of it being the second one, and I probably would as well. But if I plug that in over here, I can say, well, now I get to say I have negative 3x plus 2x squared equal to 0. I can definitely factor out an x with a negative 3 plus 2x. So I either get x equal to 0 or x equal to positive 3/2. And then I can plug those back in over here to get the corresponding y values. So if x equals 0, I'm going to get y equal to 0 squared. And if x equals 3/2, I'm going to get y equal to 3/2 squared. Yeah, I feel like it would have been more work to do it the other way. Not that that's not okay, just trying to make it easier. So we found our critical points. They are 0, 0, and 3/2, 9/4. And now we're going to do the usual thing and find the determinant of the Hessian So we're gonna get a 6x times a 2 minus a -3 squared. Which I guess we could write this as 12x minus 9 if you really wanted to plug in simplify it. So we plug in 0, 0. We get 0 minus 9, which is -9, which means we have a saddle point, which is kind of my favorite thing to happen. It's easy, we don't have to do any more thinking. And then if we plug in the other point, 3/2, 9/4. Well, we're only plugging in for x because there isn't a place to plug in y. So we're just getting 12 times 3/2 minus 9. That's going to be 18 minus 9, which is 9. So here's the downside of doing what I did. Simplifying this as 12x minus 9. If I now think about, well, if this is positive, I have to check fxx or fyy. I can't just see it immediately right there since I kind of multiply it together. I have to kind of look back here and be like, well, there's my fxx. Actually, I guess technically I don't really have to think that hard because no matter what, fyy is always positive. And so instead of taking fxx, check fyy. Fyy, which is 2, is positive, meaning we are concave up. So we definitely have a relative minimum. I would definitely recommend always thinking about the concavity because it can be easy to misinterpret the science otherwise, right? You're like, oh, the thing's negative, that means it's a minimum. No, if the thing's negative, concave down, oh, we have a maximum. I would always do that because I used to make that mistake not infrequently when I was a student. So definitely be careful there. It's really easy. It's really easy to get it right if you just do the one extra piece of like, oh yeah, we're talking about concavity. Give up, need to have a minimum. Okay. Let's look at this one. Yeah, we got time for one last example here. So let's look at this function here, which is kind of terrible. X plus y plus 8 divided by x times y. A little bit gross. Well, first off, I were doing this, I would definitely rewrite it as f of xy equal to x plus y plus 8 times x to the negative first times y to the negative first. I definitely would separate it as x to the negative first times y to the negative first, not xy parentheses to the negative first, because I know that I want to keep them separate when I take the derivative here. So my partials, fx is going to be 1 minus 8x to the negative 2 times y to the negative first. That seems terrible. And fy is going to be similar. Oh, yeah. Oh, here's a cool thing to see. Fy is going to be 1 minus 8 times x to the negative first times y to the negative second. But there's something worth observing here that I think is worth observing, which is why I said this word. This function is what we would say, this function is symmetric in x and y. Meaning if you interchange x and y, you would still have the same function, right? If I said that was y and that was x and that was y and that was x, it would literally still be the same thing. And when that's the case, I hesitate to say for sure always, but I'm pretty much sure for sure always, your critical values have to be values where x and y are the same. Or at least if not the same, you get each pair and its reverse. So like if 2, 5 was a critical point, 5, 2 would also have to be a critical point. Because you could interchange x and y and get the opposite values. But I feel like it's really, they come out to always be just the same. Like you get 3, 3 or 7, 7 or 0, 0, right? You don't get any kind of other things. Okay, this looks terrible to deal with. So I definitely don't love these negative exponents when I'm trying to solve this. So I would definitely rewrite this as 1 equal to 8 over x squared times y. And I would probably then multiply both sides by y to get y equal to 8 over x squared. Yeah, I could have done that with negative exponents. I don't like it. And then that's what I'm going to plug into this other equation here. My other equation, which is 1 equal to 8 over xy squared. I'm going to plug this in. I don't feel good about this at all. Seems gross. That's going to go there. And maybe I'm going to regret having written it like that, but oh well. 1 is going to equal 8 divided by x times 8 over x squared squared. Okay, that's not too terrible. So let's get rid of these denominators and just say we have multiply both sides by x times 8 over x squared and get x times 8 over x squared equal to 1. Sorry, equal to 8. Right, it's multiply both sides by this denominator here. So then I can simplify. I've got x times 64 over x to the 4th equal to 8. I've got 64 over x cubed equal to 8. I've got 64 equal to 8x cubed. 8 is equal to x cubed. So I got x equal to 2. And similarly, if I plug in 2 here, I'm also going to get y equal to 2. Which is great, because that's what we expected to happen. We expected the x and the y values to be the same. I should mention here, when you're solving x cubed equal to 8, there is only one real solution. There are also 2 other imaginary solutions that we are not concerned with. But just in case you're worried about like there being potentially more solutions, there are not more real solutions when you're solving a cubic equal to just a nice integer number like that. So then we got to test it. Okay, so let's see, fxx. Fxx is not my friend. Let's see, so fxx is going to be positive 16, x to the negative 3rd, y to the negative 1st. Fyy is going to be the same deal, but with y instead of x's, so it's going to be positive 16, y to the negative 3rd, x to the negative 1st. And fxy is going to be positive 8, x to the negative 2nd, y to the negative 2nd. Yeesh. That seems terrible. I would definitely rewrite this as 16 over x cubed y times 16 over y cubed x minus 8 over x squared y squared squared. And then if we plug in 2 comma 2, all right, so 16 divided by 16 is 1. 16 divided by 16 is 1. And 8 divided by 4 times 4 is 8 over 16, which is 1/2 squared. So that's going to be equal to 1 minus 1/4, which is positive. And so both my second derivatives were positive. This is going to be a relative minimum because we're concave up. Fxx is positive, concave up, relative. Neat. Excuse me. So that's pretty much finding and classifying critical points in a nutshell. We're finding the critical points and then we're just throwing them into this equation and we're seeing if it's negative or if it's positive, and then if it's positive, what the second derivatives are doing. It's usually not too terrible. Sometimes it's terrible. Like sometimes there can be functions where things get really, really messy. It can be challenging to find your critical points, but it's usually never that bad.